That was a very quick presentation. I'm sure there are going to be many questions later on when we get into the discussion phase. Thank you very much. Our next speaker is Mr. Karim Saad, and his paper is on economics, management of water treatment plant residuals. Karim is a senior mechanical and process engineer at Port Said water treatment plant owned by Suez Canal Authority. Karim has been leading and overseeing various water treatment projects for over 9 years with a strong background in design and operation of conventional water treatment plants, UF membrane-based plants, and RO desalination plants. Karim is a certified project management professional with a proven track record of preparing strategic plans, preliminary designs, technical specifications, tender documents, and quality audits. He is experienced in performing predictive and corrective maintenance of electromechanical equipment. Over to you, Karim.
Thank you. Good afternoon. We are going to talk about management of water treatment plant residuals. Okay. Here are the outlines. We are going to talk statistics of drinking water in Egypt, types of surface water treatment plant, types of treatment residuals, properties of treatment residuals, residuals treatment techniques, case studies, cost considerations, and conclusions. Okay. According to the annual bulletin of pure water and sanitation published by CAP, Central Agency for Public Mobilization and Statistics, we have three main entities for producing and transferring water: holding company for water and wastewater, New Urban Communities Authority, and Suez Canal Authority. Egypt, according to this report for the year of 2021-2022, had about 2,791 treatment plants. We could classify them based on the source of water to surface water, groundwater, and seawater. We could see that holding company for water and wastewater has about 1,089 surface water and 1,019 groundwater and 47 seawater. Nuka have 32 treatment plants, 22 for surface water and 3 for groundwater and 7 for seawater. And Suez Canal Authority has only 4 surface water treatment plants. We could say that holding company for water and wastewater produced about 9 billion cubic meter per year for 21-22, and Nuka produced about 2 billion cubic meter, and Suez Canal Authority produced about 300 million. We could classify this drinking water according to the source to the following. For holding company and wastewater and wastewater, the surface water produced was about 8 billion, and the groundwater was about 1 billion and just 56 million cubic meter. While Nuka had produced about 2 billion cubic meter from the surface water and 31 or 32 almost for groundwater and 128.5 million from seawater, and all the water produced from Suez Canal Authority was from the surface water. So if we gather all the surface water and the groundwater and seawater, we could say that the surface water produced what about 10 billion cubic meter per year from the surface water and 1 billion from groundwater, and seawater was about 185 million cubic meter per year. So the majority of water, about 89% from surface water. So we would like to focus about the treatment residuals in this type of surface water treatment plant. Okay. We could classify surface water treatment plant to conventional water treatment plants And treatment technique here is by coagulation, flocculation, sedimentation, or flotation, then filtration, or by direct filtration. And this schematic diagram for conventional water treatment plant consists of intake, water pump, distribution shaft, clarifier, sand filter, and so on. And we use the chemical disinfection by chlorine dioxide and pH adjustment or powder activated carbon, and they are optional chemicals. And aluminum sulfate as coagulant. Okay. The other technique, if we use is used to treat water by microfiltration or ultrafiltration membrane separation. And the treatment here depends on physical straining for contaminant in water by single porous material. We have here size of contaminants. We have many types of contaminants, and according to WHO, all contaminants, either chemical or microbial, could be classified as suspended, colloidal, or dissolved. Suspended material having the size of 0.1 micrometer to 100 micrometer, while colloidal has a size from 1 nanometer to 0.0 micrometer, and less than 1 nanometer it considers dissolved. Microfiltration and ultrafiltration practically have the size have nominal pore size from 10 nanometers to about 0.1 micrometer. Okay. Next slide. And this is schematic diagram for a simple ultrafiltration membrane system. Consists of feed tank, feed pump, micro strainer, and ultrafiltration pressurized. Of course, it is polymeric. Okay. Ultraviolet or any chemical for disinfection, and they optional, and treated water tank. And of course, as it is polymeric membrane, it needs some chemicals for cleaning. Okay, it normally consists of 2 acid types and 1 base type. Optional also, you can use a coagulant like aluminum sulfate or ferric chloride or something else to increase the removal efficiency of membranes. Classifications of microfiltration, ultrafiltration in hurry. We could classify them according to operating pressure, pressurized or submerged, or according to material, polymeric or ceramic. We could classify them also according to the mode of operation, either dead end or cross flow. We could also classify them according to module geometry, flat sheet, hollow fiber, spiral wound, or tubular. Almost flat sheet and hollow fiber are common on microfiltration, ultrafiltration, while spiral wound is the most common on RO membranes. We could classify also microfiltration, ultrafiltration membranes according to the direction of filtration, to outside, inside, or inside, outside. And also, AWA has produced and released the latest edition of standard of AWA P112 to characterize the minimum requirements of microfiltration and ultrafiltration membranes. Okay. We could see here that this is from AWA P112. That nominal pore size for microfiltration ranges from 0.1 to 0.5 micrometer, while ultrafiltration ranges from 5 nano to 0.1 micrometer. Particulates with size of greater than or equal to 3 micrometers. Removal efficiency for both of microfiltration and ultrafiltration should be 3 log at least. Virus removal for microfiltration should be at least less than 1 log, while in ultrafiltration should be greater than or equal to one log. And the molecular weight cutoff for microfiltration should be greater than or equal to 200,000 Dalton, while in ultrafiltration ranges from 10,000 to 200,000 Daltons. Okay? So, as majority of our surface water treatment plant in Egypt comes from conventional treatment, we are going to ask these questions and answer them in the next slides. The annual quantities of treatment residuals produced from conventional treatment treatment processes, and could we recover these residuals, and the best treatment techniques to recover them, and the cost consideration related with these treatment techniques. Okay. Okay. Types of treatment residuals in conventional treatment plant, we have three main residuals here. The first one, and the majority of residual comes from spent filter backwash water, and it ranges from 3% to 2% to 10% of influent, while coagulant sludge ranges from 2% to 4% of influent, and filter to waste. We would focus on our spent filter backwash water because it consumes, consists the most quantity of residuals in any conventional treatment plant. Okay. Properties of treatment residuals. We are treatment residuals have some properties. We could classify them according to TSS, total suspended solids. Sludge has suspended solids ranges from 5,000 to 20,000 milligram per liter, while spent filter backwash water ranges from 200 to 500. Cryptosporidium ranges from 2,000 to 3,000, while in spent filter backwash water it may reaches up to 15,000. Total trihalomethane and haloacetic acids, which are disinfectant byproducts, it may ranges according to and may differs according to the source and the degree of total organic carbon in the main raw water. And finally, the dissolved aluminum. These values, according to National Primary Drinking Water Filter Backwash Water Recycling Rule, final rule published by EPA, and disinfection byproducts in filter backwash water. Okay. Cryptosporidium is the main problem in spent filter backwash water because it has a very small size, from greater than 2 micrometer, and it has a higher resistance for chlorine. We have also another type of protozoa, like Giardia, existing in water, but it has a size greater than Cryptosporidium. Okay. According to WHO, we could see here for the type of protozoa, different types, the focus on Cryptosporidium and Giardia. We could see that resistance to chlorine is high to both of them, and the resistance in water supply is long for Cryptosporidium. Okay. Okay, so we would like to treat spent filter backwash water to produce drinking water, solid waste, and very small of liquid waste that could be discharged to sewer system, with main constraint is dissolved aluminum. Okay. According to membrane filtration spectrum, okay, we could see here that Cryptosporidium and Giardia, okay, has size greater than the nominal pore size of both of microfiltration and ultrafiltration. So we could expect that microfiltration and ultrafiltration membranes has very high removal efficiency for Cryptosporidium and Giardia. Okay. Besides, we could see that ultrafiltration has also high removal efficiency of viruses physically. Okay. and for bacteria. This is a compromise for treatment techniques of spent filter gauche water. We have to weigh either to treat them conventionally or using a membrane separation. Both of them has advantages and limitations. We could see that both of them could remove suspended solids very well, but a conventional technique has limited removal efficiency for cryptosporidium, while ultrafiltration has very high removal efficiency up to 6 log for cryptosporidium. And both of them will need granule activated carbon or powder activated carbon to remove disinfection byproducts. This is from WHO. Could see the following: that conventional clarification has very limited removal efficiency for protozoa, while for ultrafiltration we could reach up to 7 removal efficiency. While in granular high rate filtration, the efficiency of removal of protozoa depends on the process of coagulation and flocculation. Okay. This is from standard AWA M53. It mentions here different type of plant use for different ultrafiltration plants for different manufacturers, and you could see here the removal efficiency for Giardia and Cryptosporidium normally greater than 4. Okay. We have two case studies to talk about. The first one is Eindhoven production plant in Netherlands. It first started with a small pilot plant, then it extended to a full-scale plant. It uses a pressurized end membrane. We could see here that the power consumption is about 0.15 kilowatt per cubic meter, and the recovery was about 93%, and the exploitation cost amounts to 0.43 guilder, about 20 European cent for cubic meter. Okay. We could see also that they uses type of pressurized membrane with pore size of 0.3 micrometer and a molecular weight cutoff of 50,000 to 200,000 Dalton. The system consists of the full system, the full plant, consists of 4 racks, and each rack consists of 5 pressure vessels, each one with 3 modules. Okay, and because they used pressurized ultrafiltration, they needed to make a clarifier before the pressurized ultrafiltration to reduce the amount of water needed for backwashing the ultrafiltration. The other case study, but it was just a pilot scale in Germany. They used a submerged membrane, and they used clarified and non-clarified spent filter backwash water, and they concluded that non-clarified spent filter backwash water achieved the best performance. Okay, so you don't need to build a clarifier. Okay. They also used the powder activated carbon, and it didn't affect the transmembrane pressure and flux. Okay. According to cost considerations of residuals treatment, we could say that specific energy consumption for treatment residuals in conventional treatment plant about 0.2 kilowatt hour per cubic meter, while in the desalination plant at least 3 kilowatt hour per cubic meter. Treatment of residuals doesn't require further post-treatment for removal of certain elements in water like boron or remineralization or pH adjustment like in desalination plant. Complexity and cost of maintenance of equipment for residuals treatment are much less than those in desalination plant. Treatment of residuals require less much footprint as you don't need to construct intake like in desalination plant. Treatment of residuals could produce very low liquid discharge, which could be easily treated for discharging to sewer system. Treatment of residuals also produces solid cakes, which could be used in industrial application like bricks. Also, treatment of residuals reduces environmental impacts related to treatment processes. Okay. Conclusion. Residuals produced from surface water plants could be recovered to save from 0.2 to 1.2 billion cubic meter per year with very low electric power consumption. Ultrafiltration membrane separation in combination with powder activated carbon and chlorine dioxide for final disinfection could be the optimum treatment technique. Powder activated carbon is not only for removal disinfection byproduct, while also it could be used for removal any organic compound existing in water, like PFAS. Okay. Treatment of spent filter backwash water using either pressurized after gravity sedimentation tank or submerged depends on conditions of each water treatment plant and according to the designer of the plant. Treatment of coagulant sludge should be processed through thickening, dewatering, followed by drying or incineration to produce solid cakes and liquid waste, which could be further treated with spent filter backwash water. Solid cakes produced from coagulant sludge could be used in industrial applications like bricks formation. Thanks for listening.
Thank you, Karim. That was a detailed one, a lot of practical data provided.